Today we are covering section 11.4. We are going to use properties of chords of circles. So our focus today will be chords of circles. We're starting off with a theorem. We did the warm-up together, so you can cross off that space if you want to. Our first theorem in words. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. We'll also go ahead and put up our symbols that go along with our diagram. So this section over here would be the symbols part. So it starts off saying if BG is perpendicular to FD. Remember, that's what that upside down T means, perpendicular. So BG is a diameter. It's perpendicular to FD, which is a chord. Then it's saying that DE is congruent to EF. So the chord gets bisected. Bisected meaning it gets split into two congruent parts. Also, arc DG is congruent to arc GF. So that arc that is formed by that chord, it's cut at D and F, it also is getting bisected. So we could mark these pieces of the arc as being congruent to each other. It's important to remember that for all of this to happen, the chord was perpendicular to a diameter of the circle. All right, so on these examples, we are asked to find the value of x, so we are going to use that theorem we just talked about. So it's important to know that the first segment we see that goes through this point, what type of segment is that? It's a diameter because it goes through that point which is meant to be the center. Now, whoever drew this picture didn't quite get it perfectly in the center. That's okay. We still understand what they mean. That's a diameter, and this other one that slants down is a chord. Very good. So a diameter and a chord meet at a right angle, so they are perpendicular, which means that the diameter bisects the chord. So these two pieces have to be congruent, which makes this problem really easy. What does x have to equal? 6. X is equal to 6. Now all those same properties apply on number 2. We have a diameter. It passes through the center of the circle. It is perpendicular to a chord. So those two pieces must be congruent. So this time we have to set up an equation. What would that equation look like? Good. X plus 4 equals 3x minus 6. Keon, how will I solve this?
You gotta subtract x first.
Good.
On the left side, from both sides.
Mm-hmm.
Then you're gonna say 4x equals 2x minus 6.
4 equals 2x minus 6. I agree.
You're gonna add 6 to both sides to get the 2x by itself. And you should get 10x equals 2x. And then you would divide both sides by 2 to get x by itself.
Mm-hmm.
And 5 equals x.
5 equals x. Mariah predicted that for us. Very good. Questions about how we solved that equation or why we set our equation up that way? Next theorem says if one chord is is a perpendicular bisector of another chord, then the first chord is a diameter. So this is working backwards from that first theorem that we talked about. So it's proving a segment to be a diameter if it is a perpendicular bisector of another chord. This theorem is just a little bit backwards from the first one that we did. So on the first one, we knew right away that we had a diameter. This time we're using the same properties in reverse to show that we have a diameter. So if these are perpendicular and if this little chord is getting bisected, then we know for sure that this one that does end up going through the center is a diameter. That's all that one's saying. All right, on the back. In the same circle or incongruent circles, we've got two things that are true. If two chords are congruent, then their corresponding minor arcs are congruent. And it goes the other way. If two minor arcs are congruent, then their corresponding chords are congruent. So we'll fill in a diagram of that in just a minute. I'll let you get that written down first. Now on the diagram that we have, our two chords are sharing a point at B. It does not have to happen that way for this to be true. So you don't have to draw a whole second picture, but I'm just going to show you real fast. If I had made two completely separate chords, we could still use the same theorems. Okay, so they could be completely separate from each other, or they can be touching. Either way, it doesn't matter. These theorems work no matter what. So the first way says that if two chords are congruent, so that would mean that AB is congruent to BC. Those are the two chords. So if they are congruent to each other, then we would know that their corresponding arcs are also congruent. So what minor arc is formed by chord AB? It's not a trick question.
ABB.
Arc AB. So arc AB is then going to be congruent to which other minor arc?
CB.
CB or BC, whichever way you want to call it. It's that other small arc. So chords create minor arcs on our circle. It works the other way. So if instead we knew that arc AB was congruent to arc BC, then we would know that their corresponding chords are congruent. So the chord that formed arc AB is segment AB, and it would be congruent to the segment that formed arc BC, so that is segment BC. And if you want to mark your diagram with the little congruent marks, you can. If the chords are congruent, the minor arcs are congruent, and vice versa. I believe these diagrams are already there for you, so we just have to use them. Number 3 looks similar to the diagram that we were using in our theorem boxes. So our arcs and our chords have a common point at B. They marked the arcs as being congruent, which means their chords have to be congruent. So X is going to equal 12. So we didn't even need that diameter that they drew in there. We know that these chords have to be congruent, so X is going to equal 12. All right, now this next one is a little bit confusing just because I don't know that the drawing is great, but we're going to go with it. So if the chords are congruent to each other, that's what's marked, those two chords are congruent, then their arcs are congruent. So that would be arc JH is congruent to arc FG. Are we okay with that part? Now, what is the measure of arc FG?
What does that say? What's the number? What?
115?
Oh.
It's sideways. If you look at it sideways, can you see it? It's a 115. So that's the measure of this arc, 115 degrees. It comes from the central angle, which means the arc JH is also 115 degrees, which means its central angle, which is labeled X, has to measure 115 degrees. So we had to connect a few ideas to get there, but those angles are intended to be congruent. Questions about that second one? Other than the poorly made diagram? X equals 75 degrees. I would agree with that. So, oops, sorry. Let me go back. Turn on the pen. X is equal to 75 degrees. That first theorem we talked about was that if a diameter is a perpendicular bisector of a chord, or is perpendicular to a chord, it bisects the chord and the arc. So that means that this arc here is getting split in half where the diameter meets the circle. So those two pieces of the arc have to be the same. Okay, other questions, concerns? Nothing? All right, there are a couple different ways to think about this last one. First of all, we know that these lines are going through the center, so they are what kind of segments? Diameters. So we notice for sure this has to be a diameter, because if we add those two arcs together, what do we get? 180. 120 plus 60 would give us 180, right? So this has to be a semicircle. So if we instead look at the other diameter here, it includes X and the 60, which means X has to equal 120. Questions, concerns? There are other ways of getting to that same answer. I just think that's the quickest way, is to recognize that diameters give arcs that measure 180 degrees. Okay, then we'll stop our notes here and pass out our homework.